Hello everyone, today we are going to solve this continuous beam with a fixed support on the left end and a cantilever with a point load at the tip on the right end. The middle two spans are subject to a uniform load, and one span is 15 feet, the other one is 20 feet, and they both have different values for the moment of inertia of the cross section. So we're going to break this down into steps, make it a little easier to understand, and we're going to solve this using the direct stiffness method. So what I like to call step 0, right, is to formulate the problem correctly. So for beam elements that don't experience any differential displacement, for this problem, we basically have just 2 degrees of freedom, and we can just bring the force and the moment on the cantilever as external loads on the right support. The vertical load of 4 kips just goes straight into the support, and the bending moment of 20 kip feet equals to 5 times 4 from the cantilever just goes in as an externally applied moment. So first step, right, is to realize that these two problems from the point of view of the direct stiffness method are exactly the same. And so this is how we will formulate the problem. And the first step here will be to determine the local stiffness matrix of both elements, element 1, element 2, as we formulated them here before, right? We have element 1 here, element 2. This is the generic form of the local stiffness matrix for any beam element that is prismatic. EI over L times a matrix as shown here. We can apply this result to each element, element 1 and element 2, to obtain the corresponding stiffness matrix for each element. Keep in mind that we have to convert the moment of inertia to the consistent units so that it all works out consistently, right? Yeah, this member has a length of 15, this one of 20. Very well. After doing that, now we can use these matrices to assemble the global stiffness matrix. So we just have to do a mapping from local to global degrees of freedom. And we can see here that the global degrees of freedom in blue, and then the local degrees of freedom in green. So degree of freedom 2 of element 1 and degree of freedom 1 of element 2, highlighted here in yellow, are coincident. So they get basically added into the stiffness matrix, and then the degree of freedom 2 from element 2 and the off diagonals just come directly from that stiffness matrix for element 2. So if we do that, we obtain this matrix for the global stiffness of that beam based on degree of freedom 1 and 2 as defined here in the drawing, drawn in blue, highlighted in yellow, right? Very good. So that takes us to step 3, in which we basically have to compute the load vector, right? And here we break down the problem into 2 steps, one in which we apply fixed end moments at the ends of every member, and those fixed end moments basically guarantee that there is no joint rotation in that structure. And then, obviously, to restore equivalency, we have to apply the opposite of the fixed end moments at each node. And these will determine what will be the nodal displacements. So remember that the fixed end moments for a prismatic beam with a uniform load are given by this, QL squared over 12. And those are used to compute the fixed end moments for every beam element. Element 1, element 2. Those values come out to 37.5 and 66.67 respectively. Where they match, right, they are added or subtracted to obtain the nodal moments shown here as 29.17, which is the difference between 66.67 and 37.5. And then at the degree of freedom 2, we just bring in directly the 66.67. But we can't forget that we need to subtract the 20 kip feet that comes from the moment induced by the cantilever. So when doing that, we obtain the value of the force vector given here as minus 29.17 and 46.67, again in consistent units of kip feet. Right? So take a look at that for a second and make sure you understand exactly what's going on. After we do that we move on to step 4, which is simply solving for global displacements by inverting the stiffness matrix and multiplying by the force vector. We already have the global stiffness, we have the force vector, and that gives us the global displacement in the form of rotations in radians. You can compute this inverse with any type of either by hand or numerically using MATLAB or any other code, even Excel you could use. Very well. Remember, we are carrying this 1 over E, right, which I haven't specified what the elastic modulus of the beam is. It doesn't matter. It's a constant. It will cancel out at the end, but we do have to remember that. And then step 5, right? Once we have the global displacements, we map those global displacements back to local for every element, as shown here, right? For degrees of freedom 1 and 2, for element 1, and 1 and 2 for element 2. Remember, we have a fixed support at the left end of element 1, so that displacement is 0. We multiply the local stiffness matrix by the local displacements, and we obtain the local forces for each element, K times U, right? Remember these local stiffness matrix, we found them before in step 1 right here, so we're just bringing those in. And the U's are given by the local displacements, which are mapped from the global displacements that we found on step 4. Step 5 basically involves solving for the local forces of every element, and that's fundamentally a superposition from the forces we found in step 5 here and the fixed end moments. We do that and we obtain the result here shown at the bottom. And again, that's basically a superposition of the local forces and the fixed end moments. We do have to do equilibrium equations to find the shears at the ends, right? We can do that simply by doing sum of moments at one end. Let's say for element 1 here, we do sum of moments at the left end. They're highlighted in blue. And we obtain the 18.08. And then we do sum of forces to obtain 11.92 on the left end. And similarly for element 2. Okay, so that's simply superposition of local forces and the fixed end moments, right? And finally, once we have that, we can move on to step 6, in which we basically put the results of every element together to obtain the shear and moment diagrams. And we see that, as a sanity check, right, the moments that coincide have to be the same, right? So like these two moments have to match as they do match. And then you see this 20 here has to match with the 5 times 4 that we brought in from the cantilever, as you can see here. Basically, this is just statics, right? Formulating every element, doing the cuts, and writing the shear and moment equations. We can do this also by utilizing the properties of the shear and moment diagram, namely when the shear is 0, the moment is maximum, the integral of the shear gives you the moment. So like for example, to obtain here this value of 13.4, we would start with the negative 0.22 here and then add the area under the shear diagram right here. So that would be 5.96 times 11.92 divided by 2 minus 22.13 gives us 13.4. Similarly, on this end, to get the 57.4, same idea. Okay. Once we have these results, which should be fairly direct and straightforward to obtain, we go on and find the reactions, and this can be done simply by looking at the free body diagrams, right? So these are the free body diagrams of every element and then their supports. So this is element 1, element 2. These are forces that we've already found, right? And so you can see here how they add to give you the moment reactions and the force reactions at every support.